Welcome to this explainer. Today, we are popping the hood on the Hugging Face engine. We're going to find out exactly how deploying machine learning went from this agonizing months-long ordeal into a super streamlined, modular process. If you've ever wondered what's literally happening behind the scenes between downloading a model and finally getting an output, well, you are in the exact right place.
So, let's talk about this massive shift. It used to be a total nightmare for developers. Historically, deploying state-of-the-art models meant wrestling with these really complex, proprietary hardware configurations and building bespoke data pipelines totally from scratch. It was expensive and incredibly slow. But today, that entire paradigm has completely flipped. Everything shifted to a centralized hub with single script executions. It is a total game changer for who actually gets to build with AI.
Here is our roadmap for the explainer today. First, the Hugging Face hub, then transformers design, pipelines and tokenizers, handling terabyte-scale datasets, AI security, and finally, model cards. Let's get right into it.
Section 1. The Hugging Face Hub and Decentralized Collaboration.
The sheer scale here is wild. The hub is managing over 2 million models, and that's alongside millions of datasets and interactive apps. Now, standard Git protocols, they would absolutely buckle under the weight of terabyte-scale binary files. So to solve this, the hub uses specialized exit technology. This protocol does something super clever. It splits those massive binary files into unique, deduplicated chunks. This means you get rapid, lightweight transfers all over the globe without totally nuking the network. But here is a hidden networking hurdle that absolutely drives enterprise IT teams up the wall. When a corporate developer tries to download a model, that very first metadata query goes to the main.com domain. Simple enough, right? But the actual heavy file weights? Those get served via redirect flows bouncing across various content delivery networks. So if a company has strict firewalls that only allow whitelist the main domain, it completely breaks the download. You get abrupt terminations, corrupt files, the whole shebang. Basically, enterprise IT is having to completely adapt to this new, highly distributed AI supply chain.
Section 2. Transformers Design Philosophy.
Okay, as we get deeper into the core software, we find a design philosophy that intentionally breaks the rules. You've probably heard the golden rule of coding, right? Don't repeat yourself. Well, actually, scratch that. The maintainers here flipped conventional software engineering totally on its head with the one model, one file policy. They actually want you to repeat yourself. Why? Because machine learning models aren't standard software. They're static mathematical products. By repeating code, researchers don't have to hunt through 10 layers of confusing nested base classes just to debug some complex TensorFlow. Everything you need to understand a model's forward pass is right there, cleanly laid out in one single incredibly readable Python file.
Section 3. Pipelines and fast tokenizers.
Let's look at how this all builds into an API that basically acts like a highly efficient factory assembly line. Pipelines completely eliminate all that messy boilerplate code developers used to agonize over. Instead of manually handling where the data goes on the hardware, the pipeline just handles it in 3 clean phases. First, preprocessing, taking your raw text or image and turning it into framework-ready tensors. Second, the forward pass, which dispatches those tensors straight to the GPU for the heavy math. And third, post-processing. It takes those raw, completely unreadable model outputs, the logits, and decodes them back into normal human-interpretable text.
But hold on, before that forward pass even happens for text, we have to talk about tokenization. We used Rust-backed fast tokenizers, which have to run through 4 critical stages just to turn raw text into numerical IDs. First, it normalizes, cleaning up stuff like weird accents. Second, pre-tokenization, which naturally splits words at the spaces. Third, it runs a subword model, like byte pair encoding, to break rare words down into chunks the model actually gets. And finally, post-processing to add necessary special tokens. It is a lightning-fast pipeline to make sure the model actually understands what we're feeding it.
Section 4. Handling terabyte-scale datasets.
So what happens when the data you need to process completely blows past your physical RAM limits? I mean, with AI, this happens all the time. Well, the Datasets library fixes this elegantly using Apache Arrow. By utilizing a standardized columnar format, models can instantly access memory map files right on a local drive. And here's the kicker. It has a near-zero initial memory footprint. Because Arrow's binary format supports zero-copy reads, the data just flows straight from your SSD right into the deep learning framework. No expensive system-crashing duplication in your RAM required. It's honestly brilliant.
Of course, engineers still have to play this delicate balancing act between RAM and latency.
If you've got medium-sized local data, memory mapping is your best friend. Your only bottleneck is the speed of your SSD. But for massive, multi-terabyte cloud runs, you absolutely have to switch over to dynamic streaming. Now, streaming fetches data progressively over the network, which is great because it keeps your RAM strictly tied to active buffers. The downside? Random access operations become incredibly slow. Like I said, it's a constant balancing act of infrastructure.
Section 5. AI Security and Safetensors. Okay, we have reached a critical point in this explainer. We need to talk about the hidden, sometimes terrifying dangers that are scaling up right alongside AI adoption. Let me ask you, could downloading an AI model actually steal your crypto? Sounds like totally ridiculous science fiction, right? Well, the answer is a terrifying yes. On May 7th, 2026, a compromised repository actually used artificial engagement bots to game the system and hit the #1 trending spot on the hub. They perfectly cloned the official documentation to build trust. But hiding inside, a malicious script. The moment an unsuspecting developer loaded the model, it executed an info-stealer payload, silently swiping browser data, Discord tokens, and crypto wallets.
You might be wondering, how does a model steal your crypto in the first place? It all comes down to the wildly dangerous Python Pickle format. See, Pickle files aren't just passive data. They are a sequential stack of actual execution instructions. Just loading an untrusted Pickle file can trigger remote code execution. To stop this disaster, the ecosystem is heavily shifting to Safetensors. Safetensors are structurally secure. They enforce strict segregation. You get a flat JSON metadata header followed by raw binary data. That's it. It's completely stateless. Without those deserialization hooks, it is literally structurally impossible to execute arbitrary code just by opening a Safetensors file.
Section 6. Model cards for transparency.
Finally, let's explore how the ecosystem defends against ethical and performance risks down the line. Think of model cards as the vital nutrition labels for AI models. They were originally proposed back in 2018 to stop developers from suddenly discovering awful biases after a model was already deployed in the real world. They act as boundary objects. That just means they serve as a shared, accessible language bridging the gap between developers, ethicists, policymakers, and the general public, laying out exactly what a model should be used for and, just as importantly, its exact limitations.
And the best part? They go way beyond just being human readable. By baking these specific metadata fields into a YAML block right inside the repository, model cards become machine-readable audits. This means the hub can automatically parse performance scores from benchmark IDs, standardize tracking for the environmental carbon footprint of data setters, and even flag not safe for work content. It effectively bakes accountability directly into the core distribution layer of the entire platform.
So as we wrap up this explainer, I want to leave you with a pretty massive question. Are we currently treating AI models like standard software when we really should be treating them like heavily audited infrastructure? From managing terabyte-scale data pipelines and strict file structures to physically defending against remote code execution, modern AI requires immense operational rigor. As AI becomes deeply embedded in literally everything we do, how we secure, document, and standardize this foundation is absolutely going to determine its success and its safety. Something to think about, right? Thanks for exploring this with me today, and keep questioning the tech you build with.